Welcome to Organic Chemistry 2. This is the beginning of our course. This is one is a hybrid class with online lectures and in-person labs, right? So we already went over to the introduction, how the class and the course itself will be conducted. So we will have these recordings. I will try to make it the least, the not that long videos, but it's needed because we definitely need to go over many important concepts, right? So if you recall from Organic Chemistry 1, the last chapter that we covered in Organic Chemistry 1 was chapter 10 about radicals. Then it makes sense that we should continue with chapter 11, 12, 13. Then you will be wondering, why are we starting with chapter 15, infrared spectroscopy? Well, we changed a little bit because since we're going to be covering many reactions and many functional groups, chemistry functional groups, I wanted to start with, analytical techniques. Okay, why? Because organic chemistry is also about analysis, digestion of data other than melting points, boiling points, and masses, right? Which is really what we observe in the labs. But there's also instrumental analysis. So instrumental analysis can be applied to inorganic chemistry and organic chemistry, and this is the part that we're going to be using it for organic molecules, okay? So with this chapter 15 and 16, infrared spectroscopy, and the next one, which is about nuclear magnetic resonance, we will definitely elucidate the structure of a particular molecule. Right? Why? Because there are many questions about like, oh, okay, so far we've been investigating molecules based on boiling point, melting point, TLC, right? Chromatography, or, chemical tests that you guys have done in the past, right? But really not like a very deciding test to determine if you obtain a particular product in experiment, right? In a particular lab. So infrared spectroscopy and nuclear magnetic resonance, those are very powerful tools that we'll be using to determine the identity of a particular compound, right? So let's get started. So what is a spectroscopy? A spectroscopy is well, it's an analytical technique that will help us to determine the structure. So are these two the only ones, the ones that we're going to be studying, right? So you see right here, we have IR and NMR. NMR is the nuclear magnetic resonance, right? The abbreviations for that long name. And IR is from infrared spectroscopy. So what are we doing with those two? Are these the only one? No, we will have also mass spectrometry. We will also be using FID, flame ionization detection, with gas chromatography. Those are techniques that are instrumental. We're using instruments for that. And they will definitely help us to determine the identity of a particular compound, right? So when I tell you about mass spectrometry, of course, what are we going to determine with that mass spectrometry? Well, the molar mass of a particular species. So and of course, that one can be widely used not only in organic chemistry, but also in inorganic. But in this case, we will go over that, but during a lab. So we will not have a particular chapter in the lecture for mass spectrometry and gas chromatography, right? With separation of, of mixtures by gas chromatography, but we will introduce it in a particular experiment. So that will be coming later on. Okay, so the advantage of the spectroscopy, well, so if we recall, I'm gonna pause right now. If we recall from general chemistry 1, right? So remember there was a technique in which you guys had like a tube or a cuvette, what we call a cuvette. This cuvette will contain a particular analyte, or that in general chemistry 1, so in general chemistry 1, yes. So it had a color. It could be purple, could be blue, could be red, yellow, whatever. And you will inside it with, or shining it with light, 100% light in, 70% light out. So of course that percentage changes. So, but in this case, you will be saying that what happened with the 30%, right? Because 100% at the beginning, 70 at the end. So 30% of the light got absorbed by the sample. So that's why we will say that 30% is absorbed, or is the absorbance of the sample. And what happened with the 70? The 70% of the light is the one that made it through the sample. So we will say like 70% transmittance, the light that went through. So in general chemistry, we use these two techniques, UV-vis, ultraviolet visible. I will go over those two. UV-vis, we normally measure it with absorbance, but in chapter 15, we will use infrared spectroscopy. In infrared spectroscopy, we don't use absorbance. What we're using in infrared is transmittance, okay? So why? Well, with a little bit maybe to make it different from UV-Vis, because these two techniques are used in organic chemistry, to be honest, yeah. Of course, UV-Vis not that much in organic chemistry, but it can, in particular molecules, you can use UV-Vis, right? So that's just to give you an idea, right? To remind you like what is spectroscopy and then how it is measured. And the same type of analysis, it will be used in infrared spectroscopy. It destroys little or no sample. Yes, that's correct. So in your sample, your cuvette or wherever you're doing the sample, you can retrieve the material and definitely you can reuse it. Okay. And then we use it, well, light. Of course, light is what is used because it's a spectroscopy spectrum, right? So it's a type of radiation, and the radiation can be labeled or can be designated based on the wavelength, right? Wavelength is what dictates how strong or the strength of a particular radiation. Okay, so the ones that we will be covering in this chapter is infrared spectroscopy, that is going to be dealing with the vibration frequencies, okay? So that's something that is very important for you guys to remember. Infrared is about vibrations. NMR is about, here we will see only hydrogen atoms that are going to be used or detected with NMR. Right? So just to go over or to emphasize a little bit more on what it is about. So remember that when you guys had the electrons, right? So they got excited in the ground state. We call this ground state, right? So when an electron was in the ground state, it will absorb light, and then that electron gets promoted to excited state. So we call this like an electron transition, okay, or electronic transition. Who causes that? So of course the light, because the light is, remember, it's a form of energy. And who allows, what type of light? Is any type of light that can do that? No. UV light, right, which is ultraviolet light, or in some cases visible light. Those two are allowing you to do an electronic transition. In our case, we are not going to have that type of transition. In our case, remember, we're using infrared. So in infrared, we will have a particular bond, not an electron, but you can represent a bond like a pair of, right? Like a match, right? Match bond. And then those two will go to a higher or a vibrational transition. What we also call a vibrational mode. So we don't really represent like the electrons migrate because they really the electrons are not really moving to a higher excited state, but we will call it like, right, kind of like a parallel, right? So the electrons, don't think that the electrons are going to go to a higher energy level. No. So what is going to happen to the electrons or to this particular bond, right? A bond is going to be, the bonds are going to be vibrating in a particular type, right? In a particular way that we will cover. I mean, we will study in a second. Okay. So this one is what I'm just going to make sure that you guys understand. So the difference between the transition, electronic transition from the ground state to the excited state, that's caused by visible light and UV light. The same happens with IR. Infrared light can also cause that two bonds. You are not going to be transitioning electrons. Well, the bonds are made of electrons, but remember that they will be at a particular vibrational transition, what we call a vibrational mode, right? So, and what are those modes? Well, those modes are caused by this light that is going to be, this slide is just going to show you like, more or less to place you right in context, like where we are located in the case of the infrared light, right? So remember that this whole, rectangle is really all the electromagnetic radiation. Electromagnetic radiation is all the radiation that is known in Earth, in the universe that we know. We don't know what happens in another universe. You don't know if in another galaxy, maybe there is another light here. So who knows? Maybe there is more energy here. But what we have seen in Earth, or in the in other in those trips that in the rockets that they explored, the maximum they have observed is the gamma rays. There is something here which is called cosmic rays. Some tables, some authors, they consider cosmic rays, but some others not. So for example, our author for our book, Klein, apparently he does not include the cosmic rays, but radio waves, microwaves, infrared light, visible light. You see like a very small range for the visible light right here, right? Ultraviolet, X-rays, and gamma rays. The one that we will use for NMR will be radio waves. Okay, but right now we're focusing on infrared. Infrared spectroscopy uses that particular light, and you can see that it's right, less energy after visible light. Okay, so that one is the wavelength for the particular for infrared light. Okay, and we use it as wave numbers. Remember that in general chemistry for UVBs, you will say like, oh, I'm doing a reading at 500 nanometers, right? So that would be the convention, right? So, oh, my sample, I need to read at 500 nanometers. Or if you're doing a biology, like a cell culture, you want to see how fast you grow your bacteria. You also have another one. I don't know. I remember it's 560 or something. I don't remember exactly, but you always read a particular nanometer, which is the wavelength. In infrared, we don't use that. Why? Because the numbers are so large, right? Compared to the visible light, that you don't really say like, oh, my is 0.005 nanometers. No. Why? Because the infrared is very small, right? It's very large. The wavelength is too large compared to the visible, because it's less energy. So instead of saying like, oh, 3,500 nanometers, that's a wavelength, let's say for infrared. So instead of that, they use wave numbers. So the wave number is, just to give you an idea, is the reverse of the wavelength. Okay, so as you see here, is in centimeters to the -1. So instead of saying centimeters as a wavelength, you use the reverse, the inverse of the wavelength, right? So are we ever gonna do a conversion wave number wavelength? No, 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 no. So we'll just work with the data that is given to us for infrared, and then that data always comes in wave number. Never will be a need for us to do the conversion wave number to wavelength. Okay, so okay, good. So remember I was telling you about these vibrational modes, right? When a particular energy, right, gets absorbed, there are different types of vibrations, right? So just to put you in context, let's close this. Okay, so let's say this one is a molecule, right? So has bromine. So one of the requirements for a molecule to interact with infrared light is that the bonds have to be polar. So as you can see, this bond, this one is a CH bond. By nature, we know that CH bond is not that polar, but you can see that this molecule is not symmetrical, right? It's an sp2, it has a dipole moment. So this CH bond will interact with the IR light. So you will see a response. Remember, you see bonds in infrared. You don't see the hydrogen, you don't see the carbon. What you see is the CH bond. This one is bromine, okay? So if you shine this with infrared, you are not going to see the bromine, you are not going to see the carbon. What you're going to see is the CBr bond. Same thing here. This one is carbon, this one is a COO. CH. In infrared, you are not going to see the oxygen, you're not going to see the carbon. What you will see in the infrared is the COO bond. You will see the CH bond. Here you will see the OH bond. Here you will see the CO bond. Here you will see the CH bond. Okay, so it's going to be clear that in infrared you see bonds of a particular molecule. Okay, and of course this CH might be different from this CH. Why? Because this CH is not the same as this CH. So like, how come? There are CHs, yes, but the difference is that this CH is close to an oxygen. So of course this CH has a different polarity than this CH, for example, right? So these CHs are not going to have the same polarity. Why? Because one is going to be very close to an oxygen, which we know that is more electronegative. This one is maybe less polar. So it will have a different response to the infrared light. Remember, the infrared will do vibrations and they will only focus on polar bonds. Okay, so now I say like, oh, but we know that CC bonds are not polar. Yes, CC bonds are not polar, but infrared is so meticulous about the interactions that this CC bond maybe is different from this CC bond. Why? Because this CC bond is closer to an oxygen, so it will cause a response because of the oxygen, the presence of the oxygen. Okay, so hopefully that is clear, and it's very useful for us to understand this because we will have a lot of functional groups, right, that we need to study. Well, by now you guys should be familiar with this table. I gave it to you in Organic Chemistry 1 for the ones that took the class with me before. If not, you will receive this particular reference table the first day of class, the first time I see you. It's also posted on, in our platform, right? You guys can print it out, but I will give you one hard copy in class. Okay, so you have different function groups: alkene, alkyne, aromatic, alcohol thiols, ethers, aldehyde, ketones, carboxylic acid, ester, amine, and amides. Okay, these bonds can be visible by the, of course, by the IR. The alkene will have a peak because it has a C double C, OH, CO, C double O, CH of a C double O, right? C double O, COH of a C double O. All these bonds have different type of nature, so of course they will have a different IR response. Right? So now going back to the vibrational modes. So what happens with the infrared light? Once the infrared light shines the molecule, each of the bonds will do a different type of response. So sometimes maybe it will bend. Sometimes it will do some scissoring. That is a vibrational mode. Sometimes it will do some twisting. Okay, stretching, right? It will stretch, maybe it will expand a little bit. I can't do it because if I do it, I break it. But this bond will open and close like a spring, right? So though that is caused by the infrared light. And when does it do it? When this bond is polar. If the bond is not polar, the molecule is not polar overall, of course, the infrared is going to be inactive, is IR inactive. The molecule will be IR inactive. Why? Because the molecule is not polar at all. So for example, you tell me like, what happens with methane? Methane will have, right? So, let's play with the models a little bit. Methane is IR inactive. Why? Because all the bonds are the same and the molecule is symmetrical. So methane should be invisible to the IR. Why? Because there is nothing. What happens if I change this immediately with a bromine? Now it changed. Now, why? Because the molecule now is polar. So this CH that used to be non-polar now becomes polar. Why? Because of the presence of the bromine. So now this one will have an IR response. Okay, so you see how one small change in the molecule will make a molecule IR active or inactive. Same thing applies to this particular alcohol. So this one is, I will give you 2 seconds. What will be the name of this alcohol? It has 3 carbons. If it has 3 carbons, will be called propane, right? Propane, 1, 2, 3, propane. But because it has an alcohol, it will be called propanol, right? So in case of propanol, the same thing. So you guys will see this one will have a particular mode, another particular mode. And of course, are all the scissorings, all the twistings, all the stretchings, all the bendings are the same? No. Why? Because the polarity is the same. An OH polarity is not the same as a CO polarity. It's not the same as a CH polarity, right? So they will have all different type of vibrations. So that's what makes the difference, and you guys will see different responses, okay? So going back to this slide, right? So we will have different regions. I'll show you right now in a second, like what it looks like, an IR spectrum, but the IR can be divided into 4 regions. One is useless. I will just tell you up front, like this region, what we call the fingerprint region, it's really not, it contains information. Here you see the CC bonds, CO bonds, CM bonds, but it's so complicated, it's so complex that we normally ignore it. So in our case, you are not going to be using the 1400 and below. Okay, so we call that the fingerprint region. So our chapter or our IR analysis will be divided into 3 segments. This 3 segments is the high IR, the medium IR, and the low IR. Okay, the fingerprint is the one is only one on the right, so we don't count it. The one on the left, let's call it maybe left, middle, and on the right. Okay, so on the left side you will see the NHs, OHs, CHs. In the middle you see the C-triple-Cs, alkynes, C-triple-Ns, nitriles, and on the right side you guys will see double bonds, alkenes and aromatics, COO. In COO, we have a big family. We have ketones, aldehydes, esters, amides, carboxylic, and CON. CON is a particular functional group that we have not studied yet. So those are called imines. Okay, right now I'm gonna get it closer so you guys can see what's an imine. Imine is a CON. We will study those when we reach to the chapter of I think it's 19. Yeah, aldehydes and ketones. We'll study aldehydes and ketones, and then you guys will learn what is an imine. So for now, just forget about the imine. So imine you guys will not see it, but at least for future exams or for you're gonna planning on taking MCAT or GRE, yeah, you might want to know or remember what is a CON, imines. All right, okay, let's get started. So with there's a table here, so now I'm gonna be very clear with tables, reference tables. There is no perfect reference table. So what is a good reference table for me might be different from a particular professor in City College. It's different from another professor in the University of Boston, different professor at the University of, let's say, of Florida, or the professor at University of Puerto Rico. Every professor has a particular preference for the reference table. So you can see here, the OH, right? The OH bond goes from 3,200 to 3,600. What happens here? Just remember that number, 3,200 to 3,600, right? OHs. What happens in this one? For this author, OHs go from 3,200 to 3,500. Now, the big question is why, right? Why that other professor thinks that is, or that author thinks that is 32 to 3,600, and then this one is from 32 to 35. And this one even has another type of OH, right? So all the authors, they have different types of approaches or different types of references. Maybe they have seen a particular OH that has showed up, right, at that particular wave number. So that's why they report it. So my recommendation is, this one is from the textbook, for example. This is Klein. Klein thinks that we should use this, but I found this one. This one is a more complete table. You see how many data you guys have in here. This one is a little bit more limited. Okay, I'm not saying that this one is worse, this one is better. It's just giving you this one that you guys are getting as a reference table. That one gives you more options, more information. Okay, so we're going to be using, I'll show you how to use this table. And so let's see now, before we go to this particular slide. So I'll show you what is an IR. So this one is an infrared, let's say, spectrum. Okay, so here, that's exactly what I was telling you. This one is anytime that you guys are doing IR analysis, get a ruler. So here, 1400, each line is 25, 1, 2, 3. Here, 1400, more or less. It's not that accurate. Okay, for me, that's 1400. This one is what we call the fingerprint region. Should I focus on this? No. So, which is good because you see, all the IR is normally complex here. It's very, very scary on this side. I'll show you another one. See, there is not much to analyze on the left side. Most of the complicated stuff is on the right side, which is the fingerprint. But we don't need to analyze these peaks. So we only need to analyze these ones, which just makes it not that difficult, right? So you look at this. It's really not. You really have to look at this, this, and this. That's all. Or maybe this, right? What else? I'll give you another example. That's another IR. You will tell me the same thing. Oh, it's flat here. I see something here. But then this one is the fingerprint division line. I don't really have that much to look at. Yes. Yeah. Okay. So we're really going to be looking for specific points. So this one is for you guys to see what is the fingerprint region. I don't need to look at that. Does that mean that these peaks mean nothing? No, they do mean something. Okay, so they do mean something, but I mean, we don't really pay attention to those peaks. All right. Okay, so what happened with the fingerprints? So fingerprints are different for every molecule. Look at this molecule. This one is the fingerprint. Now look at this fingerprint. They're totally different. Okay, that's the fingerprint. You say, what happened? Why are these molecules so different? They're all made of carbon, they are made of hydrogen, right? Maybe this one has alcohol, but the alcohol doesn't matter because alcohol shows up in a different region. Yes, fingerprint regions are unique for every molecule except enantiomers. If you have two enantiomers, right? Remember what are enantiomers? If not, please just go to Organic Chemistry 1. We need there are compounds that are mirror images and they are not superimposable, right? They are uh, they have optical activity and they do rotate the polarized light, right? So that would be the definition of a chiral compound. So a pair of enantiomers, they should have, well, in this case, they're not enantiomers. So these two enantiomers, right? So these two enantiomers, they have the same fingerprint region. Okay, so they're identical. The fingerprint should match. Okay. All right, so let's go back to the slide. So I already show you. All right, so what happens? So no two molecules will have the same exactly same IR spectrum except the enantiomers, which will have the fingerprint region. Okay, so the simple stretching is that region. I already showed you, right? The division of the three segments of the IR. Polar bonds are usually IR active. The non-polar bonds, they will have so wiggly or no compound, right? The example of methane that I gave you, CH4, right? So it will not be IR active. So the bad thing of IR limitation, stress and limitation is like, for example, the good thing of IR is that it will quickly tell you if your reaction was successful or not. Okay, so it's a very quick technique. It's something that you just put the sample inside of the machine. The machine in 1 minute will give you already the result, and you can definitely explore your outcome of a reaction. Right? Some signals might be ambiguous. Why is that? Because as I told you, some peaks, some authors, they say like, oh, this one is the range for this functional group, and then this is the another range. The reference tables are not perfect, so that's why it can be ambiguous a little bit. So the functional group will be shown. I mean, you will see, you will determine if an alcohol is present, you will know if a carboxylic acid is present, but that's all. Okay, and then what is another one? So for example, it can be very powerful IR. For example, if I do a chemical reaction, right? So let's say that I'm doing the conversion of hexene, cyclohexene, I'm adding H3O plus, and then I'm making it into an alcohol. That's a reaction that we studied in organic 1, right? In 230. So here you will see a peak for the alkene. And here you will see a peak for alcohol. So can you explore this with IR? Definitely. Definitely. In the IR, you will see a peak for alkene. And that peak in the product should be absent. You should not see anything for that peak. Now, alcohols show up in a different region. You should not see that alcohol peak on your starting material, right? Because the starting material is not an alcohol. So it should be absent, but it should be present in your product. Now, the alkene is your starting material, should be present, but it should be absent in your product. What happens if I see something here? What would you say? It says that not all my starting material was reacted. Maybe I need more time. I need more reflux. Maybe I need to add more acid, right? So that's what it's telling me. So you can actually do like a time dependence based on infrared spectroscopy. Okay, the reaction for 10 minutes, not done yet. Use IR. 20 minutes, not done yet. That's by IR. So with the infrared, you can determine if your study material is gone or not. Okay. Now, in terms of the limitation, the bad thing of IR is that you cannot determine a structure. Okay. Remember that infrared will tell you if an alcohol is present. It will tell you if a carboxylic acid is present. It will tell you if an alkene is present, but it will not tell you the structure. What do you mean by structure? The structure is this. For example, this one is propanol. My bad. Mm-hmm. 1, 2, 3. Oh, butanol. My bad. Butanol. And this is also another butanol. It's only just 2 butanol. Down is 1 butanol. Butanol. But this one has an OH peak. This one also has an OH peak. With IR, I cannot distinguish between those two. Why? Because they have the same peak. They also have the same CHs. They have the same CCs. So you cannot really see the branching. So what about this other compound? Terbutanol. By the way, don't worry about the naming yet. So we haven't done naming of alcohol. So don't worry about naming. These are isomers, right? But infrared or IR will give me the same peak for all 3 compounds. Okay, so here we'll have an OH bond, OH bond, OH bond, CHs, 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 CC, CC, CC. So I cannot use it. Who is going to help me to distinguish between these guys? Chapter 16, NMR. Okay, the solution for structure determination is NMR. NMR is definitely a more powerful technique that will allow me to distinguish or to differentiate between butanol, 2-butanol, and terbutanol. Okay, so that would be next. That's actually a little bit more complex, but definitely more powerful and more useful for structure determination. Okay, everything clear? Remember that you can always send me an email or ask me during the labs or during my office hours. I'm always open to hold, or by email. Once again, by email is the quickest. I mean, if you are outside office hours or outside the lab, and then by all means, when you see me in the lab, please come to the desk or just call me, and then I will answer those questions. Right? This one is the enlarged view for the infrared, so it will clearly distinguish between the 3 regions. This is 1, 2, 3. The 4th one is the fingerprint region, so don't even bother looking at the fingerprint region. We are not going to study the fingerprint region, right? So we're going to be looking at each of these functional groups, okay? NHs, we have amines, alcohols, CH as well. CHs is everywhere, really. For example, this one has CHs, this molecule has CHs, this molecule has CHs, even this molecule has CHs. Okay? So CHs will be present everywhere. But there are different type of CHs. Not all the CHs are the same. Remember that there are CHs double bonded, CHs triple bonded, CHs single bonded, right? So single, double, and triple bonded. So like, oh, but how is it double bonded? No, it's not like the C and the H has triple bonded. So what happens is that the carbon can be triple bonded to another carbon. The carbon can be double bonded. The carbon can be single bonded, but the CH is present, right? So as another reference table, and let's start with the first one. So now we are with the carbon hydrogen, CHs. Now there are different type of CHs as we mentioned before. Okay, there is what we call a CHSP3. CHSP3 is a carbon that is fully single bonded. So that CH will have a particular IR. This carbon is double bonded, therefore it will have a different IR. This carbon is triple bonded, so it will have a different IR response. So we call to this type, this one that is single bonded, CHSP3. This one is a CHSP2, and this one is a CHSP. The difference is here. So, and then this is how you guys will identify each of the peaks. There is a 3000 line. Okay, 3000 line. If you see many peaks right below 3000, that means that you guys have CHSP3, okay, which is a CH alkane. If you see peaks right above 3000, that's a CHSP2 or a CH alkene. And if you see a peak way above 3000 with this particular shape, more or less, you guys have a CHSP. Okay, but remember the 3000 line is your reference line. That's what you guys will use to determine what is present in your molecule. Right? So now let's go to the example. So because I'm always very hands-on with this molecule. Okay, so let's start with this. Here you see the molecule. Okay, for now, since we are learning, I'll show you the molecule. So here's the 3000 line. Okay, So you here see the full spectrum. Yes, right, you see? Oh, the spectrum will always be labeled as wave number and percent transmittance. It will be opposite from 100 to 0. In this case, it just goes to 50 because the peaks don't make it. And these numbers are relative. So for example, this one, sometimes it goes down to 80. Sometimes it will go down to 50, right? For example, let me show you another one that has a more, example, this one, see? The peak goes all the way down to 35, right? So it varies. So don't think that, oh, the intensity tells me something. No, it's really the shape and the wave number what tells you. Don't be that worried about the percent transmittance. The y-axis does not mean much, okay? All right, so let's do an analysis. The first thing that to do, well, first is think of imaginary, right? Line here for fingerprint. Forget about the fingerprint. We're gonna be looking at the left side. So 3000 line, trace a line. Do I see peaks on the right below 3000? Yes. So you guys will do CHSP3. Okay. Now, do you see peaks around right above 3000? Yes. This one. That's a CHSP2. What am I doing right now? What I'm doing right now is called a peak assignment. So peak assignment means like this peak is this peak is that. Now, is this one, do you guys think that this one is the CHSP? Look at the shape. No, right? It's not how do you know, Professor? Well, here, the CHSP has like a kind of like sharp type of shape, okay? That is not that one that I see in this particular spectrum. How do you know that? Professor, do we have to memorize it? No, you don't have to memorize it. Why? Because here you guys will have the peaks, okay? So there are different type of abbreviation: strong, sharp, strong, broad, medium, narrow, see, narrow, strong, okay? And that's what it is, how medium, weak, strong, narrow, broad, sharp. The V is variable. You will see V somewhere. V. Maybe you guys saw it before me. You see the V somewhere? I lost it. Okay, right here. Okay, V is right here. That V means variable. Variable means that could be a strong, could be medium, we can be weak. The C-triple-N is variable. Okay, so it's variable. So it can be different intensities, heights, and then also, width, right? For those peaks. But here's that's how you guys will know if a peak is expected to be narrow or broad or sharp. Okay, so now you say, like, Professor, but here I see many peaks. Is there any way that I can differentiate between those peaks? How do you know is this one or this one is this one? It's a group. So for CHs, it's a group. Sometimes you cannot distinguish it because remember, like, why am I seeing so many if I don't have? Because remember, there are different vibrational modes. Maybe this particular peak, right? This one comes from the bending. Maybe this one comes from the stretching. Maybe this one comes from the scissoring, right? Or from the twisting. So there are many vibrational modes. So there is difficult for us to associate it with one particular vibrational mode. Same thing applies for the left side, for the CHSP2. So we don't know. Is that the stretching? Is that the scissoring, bending, rocking? It can be many type of vibrational modes. There is no way for us to tell. So in our case, for CHs, you just group them, and that will be the CHSP3, CHSP2. So is this the CHSP? No, this one is not the CHSP. Professor, I wanna see how does it look like a CHSP? Okay, right here. You want it, you got it. So here my analysis will be 1400, 1, 2, 3, somewhere here. That's the fingerprints. And 3000. Okay, 3000. Do I see peaks below 3000? Yes, CHSP3. I'm doing peak assignment, okay? Do I see peaks right below 3000? Right above 3000? No. Does that mean there are CHSP2s? No, there are no CHSP2s. Okay, look at the molecule. Do you see double bonds? No, of course. You're not expecting to see CHSP2s. Do you see CHSP3? Yes, there are many CHSP3 here. These carbons are single bonded, so they should show up here. See, all those spikes are right here for all these. Now, don't worry about the intensity because you will say like, oh, professor, here it says 5% only. Is that okay? Because in the previous case, we had about 1500. Once again, the intensity, the height doesn't really matter. Okay? It's just about maybe the vibrational modes. Who knows? This one is a CHSP. Okay, which makes sense because I have a CH in triple bonded, right? CH. This one is an SP. This one is SP hybridization. SP hybridization. This is an SP3 hybridization. SP3 hybridization. SP3 hybridization. Okay. So I see CHSP, and that's the intensity, and that's the shape, which is different from this broad, right? Round peak. We will see who this guy is, but more or less you can guess who this is by looking at the molecule. By the way, does it agree, the CHSP2? Yes, it does agree with the CHSP2 because I have a double bond. So what I'm looking at is that particular hydrogen, those hydrogens, CHs. Those CHs are here. That CH is also double bonded, so it's right here. What about that CHSP3? Well, this one is single bonded. So that's the CHSP3. So here is that, this one is this. Okay, so they are single bonded. The other one was a triple bonded. So that's why I see the CHSP SP. Right? Once again, the intensity, you might be wondering, Professor, but why, if this one is only one CH, why is this peak so intense? And this peak, if there are so many, 6, why is it so small? Is not, I mean, it's just like it's a mystery of IR. So, molecules are picky and then they just vibrate in a particular way. So they are not necessarily, they are not proportional, right, to the amount. Okay, let's go to the next functional group. Once again, you guys don't have to memorize all these numbers. You guys will use the IR and NMR reference table during the quizzes and during the exams. Okay. That's the 3000 line, the same approach, right? Here there are more examples. You guys can go over this on your own. This one is how you see, alkenes, they are saving time here. In the case of alkenes, of course, if you see the CHs, remember, this one is what you see is the CH, okay? But if there is a CHSP2, that means that it's a double bond here, right? So that C double C is seen at 1600, somewhere between 1600. Okay, so where do I find that? So here, let me see this. Okay, so we have here CHSP2, but if you have a CHSP2, for you to have a CHSP2, that means that you also have a C double C, right? This one is this one, but you have to see also the C double C. Where is that C double C? Right here. How do you know that, Professor? Because that one is on the left of the line for the fingerprint. What is the wave number for this? About 1600, 1625, 1650. So how do you know that that's a C double C? Because that's what I see from the reference table. Reference table is organized by wave number. So we're in the 1600 domain. So who is in the 1600? All these guys. C double O? No. C double C is the one. Okay, so that's where you see the C double C stretch, which is for alkenes. Do I have an alkene here? Yes, my molecule has an alkene, so I see the C double C right there. That peak is that peak. I mean, this C double C bond is right here. The CHs, the CHSSP2 are this one. The CHSSP3 are this one. Now, what are we missing? We're missing the OH. That's coming next. Okay. All right. Let's keep going. I think we'll first, oh, the aromatic compounds. Aromatic compounds are also CHSP2. Let me see if I find an aromatic. Yeah, we have aromatic here. Right. Aromatic compounds, right? This one is an aromatic compound. It's a benzene ring. So aromatic compounds, let's do the same analysis. 3000 line. Okay. There's a line right below 3000, CHSP3. Do I have CHSP3 in my molecule? Yes, many. Okay. Right above 3000, CHSP2. Do I have CHSP2? Many, yes. This H, this H, this H, all the ones that are CHs to the double bonded, right? They are all CHSP2s. Okay. Do I have CHSPs? No, no CHSP. Why, professor? If I have a triple bond, yes, you have a triple bond, but the triple bond does not have a hydrogen, right? This one is called an internal alkyne. Internal alkynes, they don't have hydrogen. Here, this one is a terminal alkyne. Terminal alkynes, they do have hydrogen. That's why you see it. Okay, you see it. You see that CHSP because it's terminal. But if you have an internal alkyne, you won't see the CH because just that triple bond doesn't have a hydrogen. Okay. Now, aromatic, right? The same way you guys had a CHSP2 that you have to see the double bonded, right? Because this guy, that's what you see. In this peak, you see that. But where do I see that double bond? Well, that's right here. And the case of aromatic, you guys will see two peaks. One around 1600 and the other one around 1500. Aromatic come in twos. Why is that? Well, because remember, they're influenced by resonance. The resonance that cause different types of, resonance structures. And of course, they can be seen. Normally, the one on the left is smaller than the one on the right. Okay, so two peaks. Now, exactly what are the values? Well, this one is around, I'm just giving you a range, but this one apparently is right 1490, more or less, maybe, right? Because it's right, you don't see it because it's right, the peak is right below the 1500, right? And this one is 1, 2, 3. Let me put a ruler to show. Okay, 1500, 25, 50, 75, right above, right before 1600. So it varies, I mean, the range, but those two are the C double Cs. C double C, C double C. That's how we'll do the peak assignment for that. That one and that. 1400 is the fingerprint region, so I don't care about that, but I can assign those two peaks. Now I say, like, professor, what about these ones? Are they are noise, right? This one is actually no noise. That one, we will go back to this particular peak in a minute, okay? You can more or less imagine, right? What is that one? We already assigned everything except this C triple C, right? So we will go back to that particular peak in a second, all right? How do you like it, IR, so far? Okay, so it's very visual. It's very visual. Now, here in aromatic compounds, you guys can see that this slide contains some monosubstituted rings, right? So some other peaks, but unfortunately, those peaks are in the fingerprint region. As we said before, we are not going to focus in the fingerprint region. So ignore them. So that is what it's telling you about the aromatic, right? Aromatic, you guys will see one small or weak peak, right? Between 1660 and 2000 and another medium between that range, right? But once again, those numbers change, but you are supposed to see two needles like this one. One and this one. I don't know why that happens. I'm sorry. I mean, this spikes when I use my mouse. Okay, so those two peaks are the aromatic. That is the CHSP2. They forgot here the label, CHSP2, and this one should be CHSP3, right? Sometimes they are even merged, so sometimes they overlap. Okay, don't think that they're always going to be the CHSP2 on one side and the CHSP3 on the other side. No, sometimes they even overlap, and the 3000 is right in the middle. Imagine the pencil is the 3000 line. Sometimes the peaks show up like this. So these ones are the CHSP3 and these ones are the CHSP2. Sometimes you can even distinguish. I mean, there is no separation like that. Sometimes they are merged. Okay, they're blended. But you should be able to trace a line, like in this case, you should be able to trace a line and distinguish between the presence of CHSP2s and CHSP3s, right? Next, here's some other examples, the alkyne. So now you see time for the alkyne. That's exactly the example I was telling you. Here is octine. Octine, according to this formula, is a terminal alkyne. Terminal alkynes will have CHSPs. So that's why here you guys see a peak CHSP. CHSP. I'm just trying to erase that. This one, happens again. All right, so the CHSP, and now you say, like, oh, professor, why is that peak so strong? Look, it goes from 100 all the way to 10%. Yes, I mean, once again, the molecules sometimes are picky, and sometimes they show up really strong, sometimes really weak. There's really nothing we can do. 3000, let me see, 3000 should be right here. Gonna be the more, oh, I hate this mouse. Look at, oh, no. Sorry about that. I know. I don't know. I hate this. It would be better by hand, but here there is a line. Just look at I'll just the laser. Yeah. Yeah. 3000 line. Imagine there is a line here, right here. So there is a peak, right? This is would be the CHSP3. Right above 3000, there is nothing. This is just the skirt, right? The skirt of the peak. So there is nothing here. I don't see peaks. So there is no CHSP2s. But here I see a CHSP, which makes sense because here I have this particular CHSP. So these peaks, right here, CHSP3 should be from the octine side, right? From this carbon chain. Now, what is that guy? 2100. 2100 is another type of peak, right? Which is for triple bonds. So where are the triple bonds? Triple bonds, let's go back here. Triple bonds are right on this domain. Normally, triple bonds are seen in the 2100s. Okay, 2100 is that's where you see the C triple C. Remember, it's different the CHSP from the C triple C. Okay, now this one is for octine. They say, like, what happened, professor? I see no peak here and no peak here. Why? Well, first is because the alkyne is internal. If the alkyne is internal, we are not expecting to see CHs because there is no CH, right? So there is no CH triple bond. So nothing here. Now, the big question is, like, why there is nothing here? Remember that I was telling you that you only see peaks when the molecule is polar. This molecule is symmetrical. You guys have 3 carbons on the right, 3 carbons on the left and 3 carbons on the right. Therefore, you are not. This particular triple bond is symmetrical. Therefore, it will be IR inactive. So you guys don't see this guy because stretch is no stretch visible because the bond is inactive. It's not polar. The triple bond is there. What happens is that triple bond is symmetrical. Therefore, the polarities cancel out. So it will be IR inactive. Then the question is, like, why? But okay, so I understand that is inactive, but how come I can still see the alkane side? Because the alkane part is not symmetrical. This CH3 is not the same as the CH2s. So they are not symmetrical on that side. Okay, but the alkyne is symmetrical. Right? So those are exceptions that you guys will notice. An alkyne, this terminal alkyne definitely is non-symmetrical. That's why you see both peaks. Okay, now I'll give you some more examples on my own with real molecules with alkynes. All right, that's the molecule, by the way. So we already concluded that there is a CHSP3, there is no CHSP2, right? There is CHSP, this guy, right? So small, right? So tiny. Let me extrapolate this. Should be around 2100. 1, 2, 3, 4. Yeah, 2100. CAC triple C. Remember to do this peak assignment, please. Peak assignment. In the quizzes, don't ask me like, professor, what do you mean by peak assignment? This is peak assignment. Okay, so you are putting and you don't need to do this. I mean, that's not needed. I'm sorry, actually. You don't need to do this. No. I mean, there is no need to do an arrow to tell me what it is. Just write what is what you see in a particular peak, right? CHSP3, CHSP, C-C-C. That peak, to be honest, I don't know what that is. I mean, that one, that peak, right? You see, right, 14, it's close to fingerprint, so I would even ignore it. Now, do I have to assign every single peak in the IR? No, you don't need to assign every single peak of an IR, okay? Remember that IR will only tell you what functional groups are present, okay? So it's basically giving you a hint of what the structure is. Maybe not the sequence, maybe not the branching, maybe not how linear your molecule is, but it will definitely give you an insight of the functional groups that you have inside of the compound. Okay, so 2100, that's going to be the C-C-C. Okay? I assign everything. Professor, do you see CCLs in IR? Let's see. According to the reference table, do I see CLs? I see CBRs, but they are very low wave numbers. So fingerprint, no, you don't see it here. CH wax, right? With an halogen alkyl halide, also fingerprint region. So these peaks, unfortunately, we lose them. So this reference line, right? From this side to this side, this is all fingerprint. So you don't even really have to bother looking at these peaks. You only have to be looking at that range, right? Because those are the most important. Those are the known outside the fingerprint region. This is not. Okay, so if you are wondering where is the CCL peak, is it this one? No, it's not that one. Maybe the CCL should be somewhere here, but we ignore it. We don't know. It will be a big question mark because they are so close to each other that you cannot really distinguish. Oh, this one is the CCL. This one is the CL bending. This is the CL wagging. This is no, there's no way you can do it. Okay. So for me, for example, I will tell you like, are we done with this molecule? Yes, we are done with this molecule. You finish the IR analysis because every single peak, or at least most of them, you assign it. This one is my CHSP, this one is my CHSP3, and this one is my C-C-C. Assign. That's all you can do with this IR. Okay, done? All right, so another triple bond. Yeah, this one. Okay, so far we assigned, right, the peaks going from left to right. I would recommend you to do that from left to right. So from left to right, I'm going here. I found that CHSP2, CHSP3, next that one, right? So we were wondering about that one. So let's say it's right here. Okay. 2200, yeah, maybe. That's the C-C-C. How do you know that, Professor? Again, so table 2200. Who is in 2200? Okay, so I have this guy, C-C-C. What else could be? A C-N. How do you know to differentiate between a C-C-C and a C-N? Well, you differentiate it because, well, first is that C-C-C is a little bit, is a lower, 2100. This one is a little bit higher, 2200. You say, like, yes, Professor, but they a little bit overlap. Yes, they do overlap. Something that you guys will receive with all your structures is that you will always receive a molecular formula. Okay? The formula will tell you, you are not going to receive the structure, of course. It doesn't make sense. You will receive a blank. You won't receive this. You receive the formula, C11H12, right? Now, my question is, like, do you guys think that this one is a C-N or a C-C-C? Imagine that you don't see this, but you have the formula. My answer would be, it's a C-C-C. Why? It can't be C-N. Why? Because N, nitrogen, is not present in my formula. If I don't have nitrogen in my formula, there is no way I can have a nitrile in my compound. So it has to be a C-C-C, right? Then the other question is like, what if I do have a nitrogen? Well, so first try to analyze. Normally the nitrogens are seen here. Since you are analyzing your IR from left to right, you will discover any nitrogen here before you even try to look at that peak. Okay, so that's why I recommend you to do the analysis left to right, because here you see OHs, NHs, right? That's what will come right next CHs. Right now we're doing all CHs, but you will discover. So if there is no C-triple-N, it will be absent. Okay, so first go by the wave number. Nitriles are normally in this part. Alkynes are on this part. They're very close, but not necessarily. So sometimes, once again, the wave numbers are preferential, so they don't have to be that accurate, right? But that's definitely a C-triple-C because of the formula, C11H12, right? All right, so any questions so far? Remember that you can always let me know, okay? If there is anything that you guys need further information. All right, let's go to the next one. OHs and NHs, finally. Good. So OHs and NHs are right here. You see more or less the approximate values. OHs and NHs are around 3,300, and they look different, even different from the CHs. You see that the CHs had like a more like a glove shape, right? Can you tell? You see like fingers like, right? Like chicken fingers, something like that, right? A little bit, or lizard, right? Lizard fingers, right? So they show up like that, right? In OHs, it's different. OHs and NHs, they are different. That's an OH peak. That's an OH peak. That's an NH peak. So OHs are broad, okay? And they're a little bit more to the left side. So OHs show up between 33 or 3,200 to 3,500, and they are broad. NHs, no. The NHs are weaker, medium intensity. This one starting strong and intense. Okay, OHs. NHs, no. NHs are medium and also not as broad, but also not sharp. They are not sharp. They are like medium width, right? Medium intensity and also medium width. Okay, so here you see the spectrum, the IR for this butanol, 2-butanol. 2-butanol, you have the OH. What is this, guys? This one should be the CHSP3, right? Because it's right below 3,000. Right below 3,000 is CHSP3 and the OH. Here, right below 3,000, CHSP3, and this one should be the OH, which is this one, isopropanol, rubbing alcohol. NHs, NH2, that's why you see the bunny ears here. Those two, that split of the two, right? Those smaller, right? Medium peaks. That means that one of them is one NH and the other one is the other NH. This guy is called a primary amine. Primary amine means that you have NH2. So you will see in the IR two twins. Well, they're really not twins, but let's call it like that. Two smaller peaks. This one is an NH, but this one is a secondary amine. Secondary amines are NHs. They have only one H. Therefore, you see only one peak because that peak is one H, right? One NH. Professor, do we have what we call a tertiary amine? Yes, you can have also tertiary amines. But since tertiary amines, so let me turn it off. Okay. Since this one is a primary amine, secondary amine, tertiary amine. Okay? Primary amine, secondary amine, tertiary amine. Don't worry about the lone pairs right now. But so in the IR, you guys will see that bond and this bond. That's why you will see in the IR two peaks like that. Secondary amine, you only have one NH. You guys will see only one peak. Tertiary amines have no NHs, so you see nothing. Okay? Clear, right? Now examples, right? Well, first let's start with the OHs. Example for the OH, that's a clear OH peak. Okay, OH. You see that one. Where is that OH? That OH is right here. You see, Professor, do you also see the CO? Yes, you also see the CO, but that is in 1100. Let me see, it should be this one. I know it because you have no idea how many IRs I have seen in my life, a lot. So that's why that number sticks to my, it's stuck in my head. So that's why, but do I need to label it? No, because it's in the fingerprint. So you don't really, I'm just telling you because it is present, because I know that it's in 1100 and normally it's a very intense peak. Okay. Okay. OHs, we're done with this molecule. OH, CHSP2, CHSP3, CCC. Perfect, done. I see everything here. Okay, good. Let's see another diamines. I have a lot of papers here. Okay, so this one is a primary amine. Okay, primary amine, see, NH2. Let's do the analysis. Fingerprint, I don't care about the fingerprint. Okay. Let me put it farther so you guys can see everything. Yeah, now you see everything. 3000 line. Okay, right below 3000, CHSP3. Right above 3000, nothing. What are these two bunny ears? Those are NHs. NH2, right? I could even write NH2 because it's two of them. Professor, that's kind of tricky because that one is almost noise. Yeah, unfortunately, once again, IR is IR, so it gives you a signal, even if it's very, very small, but you have to be very careful with the signal reading. I know that and this signal is totally different. This one is way more obvious, right? Just tell me, like, this is obvious, I can tell, right? This is obvious, I can tell. The other one, this one is really tricky because it can be good, I might see it, might not see it. Yeah, I know, but what can we say? I mean, I IR is IR, so that's the output of IR. So that's what we get from IR. Okay. What else? That's it. We don't have anything else because my compound only has CHSP3s, and NH2, which is the two, like those little hills, each one each. Do you see CNs? Yeah, you see CNs, but I think CNs is a little bit lower. Let me see CN stretch here. That's about 1300, 13 to 2400. Should be here, 13 to maybe this one. But once again, that's a fingerprint, so you don't really need to focus on this. Only look at this. What about these peaks? Yeah, they are not. I mean, you just have to look at the molecule and then see what you find. So here, I mean, we want to see really what it is. Let's see. About 15, close to 600, 1575. Let's see, 1575. Really? Ah, well, see, CHCC stretch. But this one is in the ring automatic. No, that's not. Oh, look, NH bent. Yeah, that is. See, NH bent. Look, right? Interesting. I mean, that's something I know I'm learning with you guys right now. So 1650 to 1580, that's exactly this guy. That's also an NH. Okay. And then it tells me it's a medium intensity, right? Makes sense. See? So now, do I have to label both? No, I mean, normally this one is enough for you to determine that you have an NH present. So this one is optional. You don't have to label this as NH. Okay. But no, look, I just learned something with you right now. All right. So, oh, another NH. Let me see. That one is a secondary amine. See? Secondary amine. You want to see the line bond structure, 1, 2, 3, NH. Okay, that's not the structure. So that's a secondary amine, 3000 line. CHSP3. That one is the NH. And you can definitely make a difference, right? You can tell that this is an NH and not an OH. Well, first, because your formula has no oxygen. That's clear. And second is because the OHs, they have a really round and broad peak. For example, this one is an OH. I see it right here. That's an OH. That's different from that peak. See the broad, like how broad it is. I mean, it's totally different. You can't miss, an amine from an alcohol. Okay, what else here? 1500. Let's carry. I mean, sometimes I say 1500 for the fingerprint. Here, I would say that would be the other NH, right? But once again, I mean, that's really not relevant. I mean, that's optional. This one, 1500. Those are my two most important assignments that I need to make. Good, clear. Okay, so let's see what else do we have. I think we have more OHs, and that's coming next. The OHs. There's one specific OH that is kind of tricky, but also very useful, to be honest. That's the OH, right? Really broad peak. The CHSP3s, the CO. Remember that they're telling you the CO at 1100. I see it right here, kind of intense, right? We are right now in this particular region. Great. Here, more example. That's a primary amine. You see the bunny ears right here. That's a secondary amine. One single amine. Oh, actually, that's not my example. That's not what I show you. But see, saturated CH stretch. Oh, it looks like it. You guys think it's this? I think so, right? Kind of, right? Yeah, a little bit. This one, this peak right here looks like this one. A little bit. That's about this. Yeah. They have things in common, but they don't necessarily have to be the same. All right, so the OHs. Now, why is the peak so broad? Because OHs are perfect are good at forming hydrogen bonds. So those hydrogen bonds, they create even additional vibrational modes. Because when an OH is involved in a hydrogen bonding, it does form different type of electronic interactions, right? Because remember, there are there are like intermolecular forces in play. So they are not regular OHs. They are OHs that are hydrogen bonded. So that gives like a different array of vibrational modes. So that's why the peak is so broad. So depending on the solvent or depending on the molecule, you can also see the free OH. The free OH might show up as a spike right on the left side. Right next to the OH, you might see that peak. You might think like, oh, that peak looks like the CHSP. No, the CHSP is normally like this at this particular height. This one is all the way to 3500. 3500 or 3600, that's only for OHs or NHs. So in this case, it's an OH, and of course, that one should be the free OH. So, but which one should I assign as OH? Of course, this broad should be the one with, should be labeled as OH. Okay. Carboxylic acids, that's the OH that I wanted to discuss about. Carboxylic acids, they also have OHs, right? You look at the carboxylic acid, let me see my reference table right here. You look at this one, carboxylic acids, they also have OHs. OHs will be visible also in the IR, but they create distortion. They get distorted. The OH is involved in intermolecular hydrogen bonds with the same carboxylic acid. Is involved in resonance. Therefore, that OH loses shape. So it will be showing as a really broad and distorted band. Okay, so it's a band that goes really, really broad. It can go all the way from 3500 to even 2000s. Okay, so can I predict it? No, you cannot predict it. Now, the bad thing is that sometimes the OHs, right, it also overlaps with some other important groups. What do you mean, Professor? Let's say that here you have a CHSP2. CHSP2s are expected to show up right here. I missed it. Why? Because the OH is so broad that I might lose it. I might not see it. What if I have an NH inside? You might, but you cannot see it. Why? Because the OH is so broad, so intense that it covers it. So that's also the disadvantage of the IR, is that some peaks are so broad that they might even overlap and hide some other peaks that are also very relevant for you. So that's why one of the first slides was saying that the IR might be ambiguous. That's the reason it's ambiguous, because a peak that is supposed to give you some information is covered by another peak that is more intense or broader. Okay, like, so that's the carboxylic acid. I have some examples of carboxylic acid. Just give me a second until I find it. Carboxylic, where are you? Okay, I have here my carboxylic acid. Let's pause the sharing. All right, carboxylic acid, that's the structure. Let's do a 3000 line. Useless in this case. Why? Because you can see that clearly the OH peak, broad and round, goes all the way from about 3400 to 2500. To me, this one is a hint that I might have an OH carboxyl. How do I confirm that? I can confirm that by the presence of a COO. Why? Because the carboxylic acid is the OH, but also has a COO. So the COO is this one, and that's a good introduction for the COO. COOs, or carbonyl groups. Some people say carbonyl group, so doesn't really matter. Carbonyl group is a really intense medium width. It's not sharp, it's not broad. It's a medium width, but it's really long. Okay, can go all the way down to even, I have seen it even down to 10% or even 5%. So it's really strong. And then the carbonyl, of course, is present, and that's the only indication. Can I see a peak, an OH peak like that and absent, and this guy absent? No way. Carboxylic needs to have that distortion and the COO. If you don't have both, then you don't have a carboxylic. Oh, what about if I see a COO, but I don't see this? Is that carboxylic? No. They two are connected. So the only way you can put here OH carboxyl is by seeing the distortion and you see the COO. Okay? I assign that peak. And that peak is 17, you look at it, 25, 1700 exactly. Let's look at the table. Who is exactly 1700? Here's just a lot of 1700s. COO stretch of carbonyls in general. Carboxylic, yes, see? Carboxylic acids, 1760 to 1690. Ester saturated, well, that's not. Okay, so that's exactly what I have. Let's finish that. Now, can I assign this as CHSP3? You could, but the peak is so broad that I cannot really decide. I cannot really assign it. I see some waves here. Right? Let me erase it because you might say, like, Professor, but you can still see the waves here. Yeah, I mean, if you can distinguish it, please, by all means, please do it. So label this as CHSP3, which we do have CHSP3, right? This one. This one is also CHSP3. You will have it, but you just have to, do your best, try to identify. But for me, that would be enough. This one is the fingerprint region. That's useless. You don't need to label that. And then I'm done with the assignments here. Another carboxylic acid is benzoic acid. I'm sure that you heard about that. We worked with benzoic acid a lot in the previous semester, right? Here's a distortion. Maybe this is not that round, but just by seeing a really broad peak around 3000 to high 2000s, that's for me an indication that that's an OH. Okay, and also I see that peak. You see this one. This one is the COO. It's intense, medium, right? Medium width, and also it's all the way down. So that's a COO. That's for me an indication that you have a COO. Okay. Where are the aromatics? Yeah, the aromatics should be here. One is this one should be the aromatic CCC, and this one should be the other CCC. CHSP2s, I can't see it. It's here maybe. Right? CHSP2, maybe that one, right? Because this one is my 3000. This one is my 3000 line. That should be the CHSP2. Here should be CHSP3, but I mean, do we have CHSP3? Actually, we don't have CHSP3, so we should not see it. You just get distorted. Those lines mean like, it's the distortion. But here, if you try, do your best, you could say like this one is your CHSP2. Okay, good. Any questions? If not, I mean, we're done with this particular IR spectrum. That's what we call assignment. IR assignment is by identifying each of those peaks. All right. Great. So we know what is a carboxylic, what is an amide, carboxylic, an OH, and now the carbonyl. So we're right now we're on the right side of the IR spectrum. Okay. So we're almost done. I know that this might be a little bit long lecture, but I'll try to do my best to squeeze it. But remember, but these classes, even if they are online, the regular lecture for an in-person class has a 3-hour lecture. So we should also expect that these particular recordings or lectures, online lectures, also last about the same, right? I'm not stealing minutes from you. I'm not giving extra minutes to you. I appreciate your time and you guys taking, your weekend or your nights or your days to watch these lecture recordings. All right, now let's go to the COO, the carbonyl. Now in carbonyl we have many functional groups. Okay, so if you guys see here, carbonyls, who are my carbonyls? Well, in carbonyls I have aldehyde, it's a carbonyl. Ketone, carboxylic, we just already saw it, so that's out. Ester, amides, right? They all have COO, and that is a complication. Why? Because, how do I know that a carbonyl is ketone? How do I know that a carbonyl is aldehyde? How do I know that my carbonyl is amide? How do I know that my carbonyl is an ester? At least for carboxylic acid is fine. Why? Because if a COO is with a distortion, then I know it's a carboxylic acid. But what about the other ones? That's what we're going to find out in a minute. Okay, so here there are some values for the COO, but once again they are referential. Unfortunately, the wave numbers that we have been learning, they are really not that accurate, right? Remember we were saying that the reference tables, they might not be that consistent, right? Even between authors, you might not have the same, right? The same values, but as a reference, amides. Normally, some people they call it amides, some people they call it amides. I call it amide. Just feel free to use any type of pronunciation you want for amides or amides, right? Conjugated ketones. This one is that's the more conventional. A classical COO should be either an aldehyde or a ketone, or here's a carboxylic acid, right? Carboxyl group. And all the way on the left, 1750 is for anhydrides. We will study the chemistry of anhydrides and esters. Esters are slightly higher. The red one is the classical COO. That's where conventional COO should be located, ketones and aldehydes. Amides are a little bit more to the right side. Okay. Okay, let's continue. Okay, simple ketones, right? Aldehyde, that's exactly what I was telling you about. Carboxylic acid, at least we know how carboxylic acid behave, right? That they have that distortion around 3000. Aldehydes are very, very, very important. Not that often seen, but you guys will see here, aldehydes, you have two CH signals around 2700 and 2800. Where are they, Professor? They are right here. This one is an aldehyde. Okay. Maybe a little bit farther. Yeah. Okay. Fingerprint. Ignore the fingerprint. It's optional for you guys to trace that line of fingerprint. You can just ignore. Okay, let's go this way. Nothing. No. 3000 line. Okay, CHSP2, right? It's clear, right? So right above 3000 CHSP2, which makes sense. CHSP3 a little bit, but not that much. But I see those two humps, those two hills here. They are the aldehydes. 2700, let me see, and 2800. Yeah, this one is 2750, 27. This is 2700. Yeah, this is in the 2700s. And this one is, that's 2800. How about, right? That's CH aldehyde. How do I label CH aldehyde? Like this. That's how you do the assignment. CHSP2, assign. Right? It only makes sense to analyze or look for those peaks if you have a double O. This one is a C double O. This is only telling you that you have a C double O. Right? Why? Because it's in 1725, a little bit less than 1725. Remember, each of these lines is 25. So this one is 1750, 1725, 17, right? So that peak is more on the 17, right? 1725, right? A little bit lower than 1725, maybe, right? So this is telling me that only that you have a C double O. Now, I don't know if this C double O is ketone, aldehyde, amide, carboxylic, ester, right? Definitely, I know that it's not a carboxylic acid, because if I have a carboxylic acid, I will see a distortion here, out. Now, the next one is aldehyde. How can I know that my C double O, my C double is an aldehyde? Because I will see those two humps, those two hills, 2800, 2700. Then I know it's an aldehyde. That's the way how to determine if this is an aldehyde. So the aldehyde, I need to see something at 2800 and also 2700. What about the carboxylic acid? Distortion. As you see, distortion around 3000, right? That's how you will know. Ketone is the basic one. Ketone is the one that is unaffected. It's kind of like the standard. That's a ketone. Okay, 3000 line. Nothing on the left of the 3000. Here, CHSP3. What else? Yeah, this one. See, it's kind of intense. But you see, this intensity is only 70%. I saw, right? We saw before something else that was way lower. Right? That intensity varies. This one, this intensity was all the way to 30%. 20, I mean, yeah, 30%, no, 35%. See, the C double O intensity varies. So this one is weaker, right? C double O. Now, how do I know it's an aldehyde, ketone, carboxyl, amide, or ester? Okay, it's not an aldehyde because I don't see anything around 2700. See, this is 2700. Let me see, 2750 around here. Nothing. So it's not an aldehyde, not aldehyde. Well, you don't have to write this, but I'm just writing for you guys to know. Not an aldehyde. Because I don't see anything here. I know it's not a carboxyl because I don't see the distortion, right? So this one is a ketone and it makes sense. Look at the structure, it's a ketone. Good. All right. Another example, I had another one, very interesting. Okay, so how do I know? Is it possible to have a C double O and an OH at the same time? Yes. And this is not a carboxyl. Look, you have a C double O and an OH. You have the C double O. But I have an OH. Is this a carboxyl group? No, it's not a carboxyl group. Why? Because to be a carboxyl, this OH should be what? Should be distorted. It should be stretched out. And it's not the case. Therefore, this OH is not connected to the C double O. It's not associated with the C double O. So if it's not associated, forget it. It's not. That means that the OH is somewhere and the C double O is somewhere else, which is the case. The C double O is on the left side and the OH is all the way on the other side. This is a ketone and this is an alcohol. So it is possible. You can have a C double O and an OH and be totally different entities. They don't need to be carboxyl all the time. Just finish labeling this. CHSP3, no CHSP2s, OH, C double O. And that's fingerprint, right? And we finish the assignment for this compound. Make sense? Please, once again, let me know you guys have questions. Amides. Amides. Okay, in the case of amides, we follow the same rule for nitrogen. Remember for amines, we were saying that you have a primary amine, secondary amine. You also have primary amides, secondary amides. So in this case, you guys have a primary amide or an amide, right? So that means that you guys will see NHs, and those are the NHs right here. NH2, two bunny ears, 3000 line, CHSP3. This is not an, well, I see the C double O right here, and that's actually a little bit lower. 1500, 1525, 50, 75, 1600, 1650, more or less, right? See, between 1650 and 1625, 16, what, 30. Okay, that's a C double O. Is slightly lower compared to this one, right? For the ketone, which is more 1750, 1700. See, this is more 1700, and that's more 1730. Sorry, 1630. So that's an amide. Okay, so amides will be like that, C double O, amide. Okay, yep. CHSP3, and that's the fingerprint region. Now, Professor, could it happen the same thing that you have a C double O and then the NH2 might be somewhere else? Yeah, you can also have the same case. So does that mean that these guys also get distorted? No, they don't get distorted. Amides, unfortunately, they don't have that property as the carboxylic acids. Carboxylic acid, because of the hydrogen bonding, they do. But in the case of amides, this hydrogen bond is not as strong as in carboxyl, so they don't really get that distorted. Okay? So you don't see it. So is it going to be tricky if I have those two? Yes, it was going to be tricky. Then you will have to use NMR. NMR will help you to distinguish between this case and this case, right? When the COO and the NH2 are in an NMite, and then when the NH2 and the COO are totally complete, right? Totally different functional groups, okay? Okay, that's an amide, primary amide, I mean the terminal amide, and an internal amide, so, not internal, my bad. An amide that is secondary, 3000 line, and that's the, right? And that's an NH. Only one hill. Therefore, it's only one single NH. And here I have the COO. 1500, 25, 50, 75, 1600, 1625, 1650. Yeah, about the same thing, 1625. Okay, COO. That's also going to help you. That position of the COO tells you have an amide or not. Because it's kind of obvious for the COO of an amide. It normally gets really pushed to the right side, right? As opposed to a conventional COO, which is a more solid 1700. Okay, those two, definitely the conclusion is that you have an amide. And of course, the CHSP SP3. Good. Any questions? Remember that you can always ask me questions during the lab, by email, or during office hours. Here are some other cases, conjugation, right? Esters are a little bit more complicated. They're higher in the wave number, right? 1740. But also you will distinguish esters from the NMR. NMR will help you more with ester. Ester, unfortunately, it will look a lot like a ketone. It's not going to look that much like the other one. So the difference I was telling you applies to carboxyl, amides, aldehydes, right? Those are the ones that you can distinguish with infrared. In the case of ketones, that's the baseline, and esters. Esters are really, really similar. So they're kind of like difficult to differentiate from each other. So for those two, I would recommend you to use what? To use NMR. NMR, which is our next one, it will be the one to be used. Okay, so this one is a ketone, CHSP3, right? There is nothing here, that's noise. COO, 1718. So it's a very solid COO, and it's a ketone. Okay. Could it be an ester? Yes, it could be an ester. Yeah, by all means. But because of maybe of the number 1720, right? 1720, yeah, that makes it a more of a ketone. But once again, those numbers are just referential. We cannot really stick to that. Aldehydes. The aldehyde you see this 27 20 and it's 2820, right? Those two small hills, right? Those are the CH aldehydes. This one is the CHSP3 COO. All right, that's noise. Carboxylic acids, right? Just go one by one. Just please just entertain your view with this. That's COO. Yeah, I say like, Professor, this one looks like two of them. What happens, right? Yeah, MI sometimes they split because of the resonance. There is an active resonance. Remember that nitrogen is a perfect nucleophile, so it will donate electrons readily, right? These electrons will go back and forth. So that causes some changes in the COO. So sometimes the COO will be with the minus, sometimes without it. It will make a difference between the because of the resonance. That happens sometimes. Sometimes happens with the amides. Nitriles, like remember the nitrile is a little bit more intense. I don't have a spectrum for you to show, but this one is very clear. But nitriles are more on the 2300, right? 2300. So that's how you guys will differentiate, identify the nitrile, the nitrogen. Okay, so of course your formula needs to have a nitrogen, and something that we will see right after this, it will be degrees of unsaturation. You also will use most of your unsaturation, so meaning that you need to have multiple bonds. Okay, that's C triple N. I would definitely use the C triple N, I mean the nitrogen, if I find in my formula nitrogen and I don't find a nitrogen, an amine. So then if I don't find an amine or an amide here, right, the NHs, then where else can it be? Well, it could be as a nitrile. Maybe my nitrogen is as a nitrile. Okay, so some other cases, you know, for the alkyne, this one is a terminal alkyne. Terminal alkyne, you should see the CHSP and you will see the C triple C. Here, nitrile. This is how you differentiate between a nitrile and an alkyne. Alkynes are normally 2100, whereas nitriles are in the 2200s. I would say, so far what I have seen in the literature, I have seen a lot of alkynes and nitriles. They are very consistent. So that's the good thing of the nitriles, is that they're always are good and strict 2200s, and the alkynes are strict 2100. Okay. Degrees of saturation. Okay, this is a formula and that's gonna help you a lot. Okay, so in the case of degrees of saturation, is that the presence of you know, double bonds or rings in a particular compound. There's a formula that I will. Okay, so let's do the example. We're almost done with the class, with the lecture, but let's say DUs. We call it DUs, degrees of unsaturation. Degrees of unsaturation. What is a degree of unsaturation? The unsaturation is the presence of pi bonds or rings. And that's very important for structure determination, because you guys will receive most likely a formula. So I will give you a formula. I will pick one of these random. C5. They tell me C5, a molecule has a formula of C5H10O2. Okay. They tell me determine the number of degrees of saturation. There is a formula that is 2C minus 2 plus H. No. 2C plus my bad. 2C plus 2. Let me see here. The formula is, I mean, I don't want to. They use a different formula. 2C plus 2 minus H plus N minus X divided by 2. That formula, remember it, please. It's not written on the slide, but that one I'm doing in the lecture. 2C plus 2 minus H minus N minus X divided by 2. Do I have to memorize the formula? Yes, you guys have to memorize the formula, unfortunately. Oxygens, they do not cause any changes in the DUs. Okay, oxygens are silent. So what you're going to do is apply that formula here. 2 C's, twice the number of carbons, 5. 2 times 5, 10, plus 2 minus the number of hydrogens, 10, plus the number of nitrogens, none, minus the number of halogens. These are halogens. They are not halogens. Divided by 2. 12 minus 10, 2. 2 divided by 2 equal to 1. That means that this compound has one pi bond or one ring. That's very important. Who is that compound? That compound is this, C5H10O2. Does it have a one pi bond? Yes, it has a pi bond. Okay. Another one. Let me see another one right here. One. Okay, this one. C3H5 ClO2. Okay. The formula is 2C plus 2 minus H plus N minus X divided by 2. All right. 2 times carbons. Oh, come on. Focus, focus. Okay. 2 times carbons, 6. 2 times 3, 6. Plus 2. Minus hydrogens, 5. Plus nitrogens, none. Minus halogens. I have one halogen. Minus 1 divided by 2. 6, 8. 8 minus 6, 2. 2 divided by 2 equal to 1. 1 degree of unsaturation. That means that my compound has one double bond, sorry, has one pi bond or has a ring. Okay. Another one, let me see. The one, okay, this one. C8H8O. Okay. I'm not going to show you the formula. Hopefully you remember. 2 times carbons, 2 times 8, 16, plus 2 minus number of hydrogens, 8, plus nitrogens, none, minus halogens, none, divided by 2. 18, 18 minus 8, 10. 10 divided by 2, 5. 5 DUs. Okay, this is a complex degree of saturation. It's high. How can you have a high number of degrees of saturation? Because you guys maybe have a benzene ring. Benzene ring has what? Benzene ring has 3 double bonds. That's already 3 DUs. And it has the ring. That's 4 DUs. So this compound already has 4 degrees of saturation. Who is that compound? This guy. How many DUs here? The ring is 1. This double bond, another one. This double bond, another one. This double bond, another one. This C double O, another one. 5 DUs. Okay? What about this one? How many DUs? How many pi bonds or rings? No ring, no double, no double. Here, one double bond, 1 DU. Okay? Let me see another one. How many in here? How many DUs? The ring, 1 DU. This double bond, 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 5 DUs. 5. Okay? That's how to do it visually by looking at the molecule, or you can do it by the formula. There are 2 ways how you guys can determine the DUs, by formula or by being given the, the molecule. Okay. Another one that has a very complex, where are my triple bonds? Okay, this one. This one. Let me erase it, clean it up. Okay, I'll give you a second. You guys determine how many DUs are here. Well, that's the formula. I'm gonna hide it. All right. How many DUs here? Count it. 5 seconds. Okay. Well, I covered it. I was hiding it. So 5 seconds. Okay, so let's see. Let's test it. Well, by formula, let's do it. C11H12. By formula, 2 times carbons, 22, plus 2, minus number of hydrogens, 12, divided by 2. 24, 24 minus 12, 12 divided by 2, 6. Okay, let's test it. According to the formula, it's 60 U's. Let's test it here. The ring, 1. This double bond, 2. This double bond, 3. This double bond, 3. This pi bond, 5. This pi bond, 6. 60 U's. You say, Professor, what happened with this one? This is not a pi bond. This is a sigma bond, right? This is a pi bond, and the other one is a pi bond. Clear? 60 U's. It matches the calculation here, 60 U's. Another one that you guys have to see. Okay, this one. For this one, this molecule has only one DU, right? Why? Because you only have one double bond. This one, one DU. All right? Let's do the formula. C3H6O. 2 times carbon, 6 plus 2 minus hydrogens. Yeah. 6 minus 6, 2 divided by 2, 1. 1 du, which is exactly what we predicted. All right? I'll just give you a few more examples before we finish. Okay, so let's say that I have this particular compound. How many DUs here? Benzonitrile. How many DUs? The ring, 1. This double bond, 2. This double bond, 3. This double bond, 4. This double bond, this triple bond, 5. This double bond, 6. 6 DUs. This one. Let's go to this one. This ring, 1. This ring, 2. This C double O, 3. Okay. Not bad, right? Anhydrides. Yeah. This one. This double bond, 1. This double bond, 1. This double bond, 3. 3 DUs. Okay. Another one. Oh, well, fuse rings. Let's see. Why not? 1 ring, 2 rings. Oh, my bad. This double bond, 3. This double bond, 4. This double bond, 5. This double bond, 6. This double bond, 7. 7 DUs. Okay, let's test it. C5, no, 6, 7, 8, 9, 10. C10. H's, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Carbons, 2 times carbons, 20, plus 2, minus 8. Unless I miscounted, but let's see. 22, right? Divided by 2. 22, yeah, no, it's fine. 22 minus 8, 14. Yeah, divided by 2 is equal to 7. Yep. You guys have 7 DUs, right? 20 because it's, right, 2 times carbons, 20 plus 2 minus 8. 22 minus 8 is 14. Yeah, 14 divided by 2, 7. Good, great. Bicycles. How many DUs? I think 2, but let's see. You never know with these bicycles. 1, 2, 3, 4, 5, 6, 7 carbons. C7. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's really how I make the problems for the quizzes and the questions, really. I solve it on the, on the go. I mean, it's really not, there is no secret book that I use. Okay, by the formula, 2 times carbon, 14, plus 2 minus hydrogens, 12. Yeah. Yeah, 2 degrees of saturation. 16, right? 16 minus 12, 4. 4 divided by 2, 2. 2 degrees of saturation. because it's a bicycle, right? Okay, makes sense. Good. So this one is very important. Right now, maybe it doesn't really make much sense, but I mean, definitely will help you to determine the structure of a lot of compounds. Okay, now let's go to the application of IR, and that's really the end of this particular lecture. Let's go to the slides. I think the slides are about to finish. Okay, how to use it in synthesis, right? So this is an alkene and an alkene, and it's a conversion, right? So you with concentrated acid, you can isomerize that alkene and then get a different isomer. So here, you see you have a terminal alkene. This alkene has hydrogens. So technically, you should be able to see CHSP2s here, which is what you see. That one is present. And you see the CCC present. Now, what happened with the product? You don't see any of those. What happened? Well, you lost the CHs, double CHSSP2, absent. But now, what happened with the CCC? Why I don't see it? Because the molecule is symmetrical. Remember the symmetry? Symmetry cancels out many of the IR peaks. So that's what really happens with that's what happened with that peak, right? For the CCC, which is supposed to be seen around 1600. Okay, so that's another let's see. Yeah, compound one. So what is compound one? What do you guys see in compound one? Okay, so I see something around this is 300, 3000. Each box I think is 100. 31, 32, 34. No, 31, 2, 3, 4, 3400. No, that 3400 doesn't really. That's a C double O. For me, it's a ketone. It's just a ketone. Let me see. Cyclohexanone. See? Now, how do I know? Are we expected to predict the name of the compound? No, you just have to draw it or you can propose it. But remember that ketone, I'm sorry, IR doesn't give you structure. So unfortunately, you won't get the structure from the IR. The IR, the only thing is going to tell you, oh, you have a ketone, you have an aldehyde, you have a carboxyl, you have an alcohol, you have an amine, right? But in this case, I only see a C double O, and that C double O apparently is a classical C double O, meaning that it's either aldehyde or ketone or carboxyl. Why? Because it's exactly in the 1714. If it's amide, it will be 1600. If it's ester would be high 1700s, right? In this case, it's a low 1700s, so it's an aldehyde ketone and carboxyl. I know it's not a carboxyl because I don't see distortion, and I know it's not an aldehyde because I don't see the two tiny peaks, right? The peaks around 27 and 2800. So it should be a cyclohexanone. So let's do also the DUs. In DUs, 12 plus 2, 14, 14 minus 10, 4 divided by 2, 2. 2 DUs. The cyclohexanone, for the ones that are not familiar with cyclohexanone, this is cyclohexanone. Okay, so, okay, let's go to the next one. Oh, okay, to me, that's an amide. This is an amide. How do you know, Professor? 1650. 1650 broad, intense, is a COO amide. And it's a COO amide with an NH2 because I see the NH2 right here. CHSP3. So let's see who that is. DUs C3 6 plus 2 minus 7 plus n plus 1 divided by 2. So 8, 9 is 1 DU. Yeah, 1 DU because I have the COO. Propanamide. Yeah, propanamide is the one that it doesn't show me the structure, unfortunately, but propanamide is this. Okay, so you guys have the CHSP3s, the COO, amide, and the NHs, right? The two NH2s, right? The NH2s, which are right here. Next, another one, right? Okay, 2246. To me, that looks like a nitrile, right? Remember I was telling you that nitriles are more 2200s and alkynes are more 2100s. So to me, it's a nitrile. Anything else? I don't see anything else other than CHSP3 and nitrile. Let's see. C6H11N, okay, 12. 12 plus 2 minus 11 plus 1. 4 divided by 2. 2 DUs. Yeah, could be a nitrile. Hexane nitrile. Yay. Good. I better get it right, right? This one, I see those two peaks, 1685. Amite, acetophenone. It should be because of the resonance. Oh, yeah, that's 15. Those are the two aromatic acetophenone. This is acetophenone. Okay. Now this one is a little bit confusing because it's 1685. 1685 looks like an amide, but your compound has no nitrogen. Doesn't show you, but doesn't show the formula. I mean, if you show the formula, you can distinguish between an amide, right? But this one doesn't really, but that's okay. All right, so here we have many more. My recommendation, what you guys can do is just Google this to see the structure. See the structure and try to identify in every peak with what you see the function group of the compound. Okay, this one is good because this one tells you this one is a carboxylic acid. See, that's why the peak is very distorted. That is C double O. That is C double C. This is the C double C. This is C double C. CHSP3, I cannot see it, unfortunately. What else is here? I see a double bond. Hexadiene, see? Diene is an alkene, double bond. I'm not gonna go that complicated. You don't have to with IR. I'm not really expecting you guys to, I'm really not expecting you guys to determine the structure or give me a name. Okay, and the last thing is like how to use IR to distinguish between two molecules. So let's say that you guys have, how will you use IR to distinguish between those two molecules? Okay, so you asked me that. I would say like how to use IR for that. Okay, here I would expect to see a peak around 1710. And strong, strong, and medium width, right? Medium width. This one, I should expect a CDOH around 3300, broad and strong. That's how I would use IR to differentiate between those two. Okay. What else? Okay, another example. How will you use IR to differentiate between NH2 and, you see, this one? Well, I can use the peak around 3200 or 3300 because they are exactly the same. What I can use is like here, I should observe a peak around 1680. And here, I will not see anything around 1680, right? I can use that peak because that peak is present in both cases. NH2, NH2, 3300. Both of them will show up. So I cannot use that as a differentiation. I cannot differentiate based on that. Okay, another one. I think we went over that a few minutes ago. Okay, can I use the COO? No, because the COO is the same. 1700, 1700 are the same. I can use that. The difference is the OH. This OH will be like around and so on, a strong peak around 3300, well defined. Whereas the OH here is going to be what? It's going to be distorted. It's going to be distorted more or less above 3300 all the way to 2500, right? Why? Because this is a carboxylic acid and this one is an OH, it's an alcohol with a ketone completely separated. Okay, so those are questions that you guys might get from this. In addition, right, to identify the peaks from the spectra, right? I'll show you the spectra and I tell you, what do you see here? Oh, I see an OH. Oh, I see a CHSP3. Oh, I see a CCC, right? Things like that, right? So that's what is expected for this. There is not much to say or you know uh to complete. We will have a lab. There is a lab session, which is a dry lab about infrared. We will practice more. There will be a practice package, so that's why I mean, even though I like to do a lot of examples during my lectures, so there's really something that we are never going to be missing in our lecture is that I do not only lecture but also examples, practice, hands-on. Okay, so that's why I use my document camera a lot for you guys to feel like you are in front of a whiteboard, right? For me, like lecturing all the time. All right. So hopefully you like this lecture. This is the beginning. I promise I'll be shorter for the next ones. I'll do my best, but let's see how we go. See you in the next chapter, chapter for nuclear magnetic resonance. Thank you. I'll be in touch soon.